So think about the last time you found yourself just completely disoriented in an unfamiliar city.
Oh, yeah. Best feeling in the world.
Right. I mean, you didn't look for the North Star, and you certainly didn't, unfold a giant paper map on your steering wheel.
Nobody does that anymore.
No, you just pulled out your phone, opened a map app, and waited for that little glowing blue dot to appear.
And once it stabilizes, you instantly know exactly where you are.
Exactly. A total sense of certainty. We treat that glowing dot like it's a fundamental law of nature, like gravity.
Right, but it's not. I mean, the infrastructure creating that dot is completely invisible.
Invisible and floating 12,000 miles above your head.
Which is pretty terrifying when you actually think about it.
It is,
Yeah.
because if that invisible web of signals were to suddenly just, fall silent, you wouldn't just lose your driving direction.
No, that would be the least of your problems.
The entire global financial system would basically experience an instantaneous catastrophic freeze.
Cellular networks would just collapse.
Power grids would desynchronize, and the modern military, their entire operational doctrine would be thrown back into the analog era in literally seconds.
Yeah. It is, without a doubt, the single most critical point of failure in our modern infrastructure.
So that's what we are getting into today. Welcome to the deep dive.
Glad to be here.
We are pulling our source material for this deep dive from two incredibly thorough foundational texts.
The real heavy hitters for this topic.
Right. First, we have the United States Army Space Reference Text. That's going to give us the rigorous mechanical and historical baseline.
And then we are layering in the strategic side using Joint Publication 314, Joint Space Operations.
So our mission today is to basically tear this invisible system down to its bolts.
Figure out how it actually works.
Exactly. We want to explore the Cold War history that birthed it, the quantum physics that make it possible, and the huge global architecture required to keep it running.
And of course, the terrifying realities of navigation warfare, because people are actively trying to dismantle this thing.
They really are. And, looking at this from your perspective, a master's level strategic view, this is all about positioning, navigation, and timing, right?
Yeah, exactly. Positioning, navigation, and timing. It is the absolute foundational pillar of joint all-domain operations.
Which basically means coordinating everything at once.
Right. It's the invisible connective tissue. It allows a joint force commander to synchronize a carrier strike group in the Pacific, an infantry unit in a city, and stealth aircraft in contested airspace.
All down to the exact nanosecond.
Precisely. To outmaneuver and outstrike an adversary today, you absolutely rely on this continuous stream of data falling from the sky.
Because modern military doctrine just assumes absolute precision now.
Oh, completely. The military assumes an artillery shell will land within feet of its target. They assume radios will connect securely despite massive interference.
But understanding positioning, navigation, and timing means understanding how that assumption is engineered.
And more importantly, how incredibly fragile that engineering actually is.
Right. So to get how fragile it is, we really need to look at how it started. It was born out of this very specific existential crisis in the 1950s.
The Cold War paranoia was at its peak.
Exactly. The United States Navy was aggressively developing the Polaris submarine program.
Hiding nuclear missiles deep underwater for months at a time.
Which is great for deterrence because a submarine's best asset is its invisibility, but there's a huge catch.
You can't fire a ballistic missile accurately if you don't know exactly where you were starting from.
Right. The fire control system needed an exact location in the ocean. But if the sub surfaces to take a celestial reading with a sextant,
boom, you've instantly compromised your position. Everyone knows where you are.
So they needed a way to pinpoint their location passively without broadcasting a signal or using visual landmarks.
And that is where the Applied Physics Laboratory at Johns Hopkins University stepped in.
They developed something called transit.
Yeah, transit. It was literally the world's very first satellite navigation system. And it relied on this brilliant application of the Doppler effect.
Okay, so break that down for us. How did the Doppler effect work with satellites?
So the satellites broadcast a continuous radio signal. As the satellite orbits toward the submarine, the frequency of those radio waves compresses. It shifts higher.
Just because it's moving toward you.
Right. And then as the satellite passes overhead and starts moving away, the frequency stretches out, shifting lower.
Oh, so that is literally the exact same thing you hear when an ambulance drives past you on the sidewalk.
Exactly. The pitch of the siren sounds higher as it comes at you, hits normal pitch right as it passes, and then drops to that lower groaning pitch as it speeds away.
Okay, so how does a submarine use that to find itself?
Well, the Navy engineers designed computers that could measure that exact shift in the radio frequency over about 15 minutes.
While the satellite is passing over.
Right. By measuring the curve of that frequency shift and knowing the satellite's exact predetermined orbit, the sub could mathematically calculate its distance from the satellite's path.
Which ultimately pinpoints its latitude and longitude on the surface of the ocean. That is so clever.
It was revolutionary. But transit had a pretty severe limitation.
It only gave them a two-dimensional fix.
Exactly. Latitude and longitude are fine if you are a submarine operating at sea level, but it completely lacks altitude data.
Which is practically useless if you are trying to guide an aircraft or a missile through the atmosphere.
2 dimensions just won't cut it for the Air Force, which is why the other branches of the military were running their own parallel programs at the exact same time.
Right. The sources mention the United States Army had a program called sequential collation of range.
Yeah, because the Army had a geodetic problem.
In the 50s, our understanding of the Earth's exact shape was actually surprisingly flawed.
Really? We didn't have the map totally right.
No, because the Earth is not a perfect sphere. It bulges at the equator, it has massive gravity anomalies.
Oh, wow.
And the Army needed to map land masses and islands with extreme precision so that their intercontinental ballistic missiles would actually hit the right targets. I mean, that makes sense. You can't hit a target on another continent if you don't know exactly where that continent is relative to your launch pad.
Exactly. So the Navy is tracking subs in 2 dimensions. The Army is trying to perfectly map the oblate spheroid of the Earth.
And the United States Air Force is over there trying to solve the three-dimensional problem.
Right. The Air Force was testing a concept called Program 621B. It used pseudo-random noise codes to measure continuous range.
And that finally unlocked the ability to calculate altitude.
Yes. But as you can imagine, having 3 different branches pouring resources into distinct, totally non-interoperable programs was a mess.
A completely fragmented environment.
So in 1973, the Department of Defense finally stepped in. They directed the branches to unify all these puzzle pieces into a single, comprehensive architecture.
And that unified architecture became the Navigation Satellite Timing and Ranging System.
Universally known today as the Global Positioning System.
So they spend the next 2 decades designing satellites, writing software, launching the constellation into orbit.
It was a massive undertaking.
But the true paradigm shift, the moment the world realized warfare had fundamentally changed, was during the 1991 Gulf War.
Operation Desert Storm. It was the ultimate proving ground. Even though the Constellation hadn't even reached full operational capacity yet.
The terrain in the Iraqi theater was just a massive navigational nightmare.
Totally featureless. Just a trackless sea of sand, no roads, no mountain peaks, no rivers to use as a handrail.
So traditional map and compass navigation, especially during a sandstorm or at night, would be painfully slow and highly prone to error.
Units could easily drift miles off course. You're risking friendly fire or totally missing operational objectives.
But the coalition forces had access to the early satellite constellation, and the soldiers realized the advantage instantly.
Oh, yeah. The military supply chain actually couldn't keep up with the demand for military-grade receivers.
Right. I read that troops were calling their families back in the United States, begging them to buy commercial civilian-grade receivers and mail them to the front lines.
It's true. The tactical advantage was just absolute. Coalition armored columns were executing massive, sweeping flanking maneuvers through the open desert in the dead of night.
Arriving at precise coordinates to completely annihilate Iraqi units.
Units that genuinely believed the desert was impassable. And the air component was using it to guide air-launched cruise missiles down the streets of Baghdad.
Right through the windows of specific command bunkers. It proved that satellite navigation wasn't just a map.
No, it was a lethal weapon system. The precision shocked the whole world.
And we just take that precision for granted today. But the physical science making it possible is mind-blowing.
It really is.
I mean, you have a metal box floating thousands of miles in the vacuum of space, telling a piece of silicon in your hand exactly where you are on a spinning planet.
It feels like magic. But the United States Army Space Reference Text lays out the mechanics of it. It's all about measuring pseudo-range using time-synchronized radio signals.
Okay, so the whole architecture rests on a basic physics equation, right? Distance equals rate multiplied by time.
Exactly. The satellites are basically flying radio towers, constantly broadcasting a specific signal. And We already know the rate that signal travels.
Because radio waves are electromagnetic radiation, so they travel at the speed of light.
Right. Roughly 186,000 miles per second.
Okay, so the rate is a constant. The receiver in my hand just has to figure out the time.
Yes. It's exactly like calculating the distance of a thunderstorm.
Like when you see a flash of lightning and you immediately start counting the seconds.
That's the perfect conceptual model. You know the speed of sound, so if you count 3 seconds before you hear the thunderclap, you can calculate the distance to the storm.
So my phone is basically listening for the electromagnetic thunderclap from the satellite.
Exactly. The satellite imprints a highly precise timestamp onto the radio wave exactly as it leaves the antenna.
And when my receiver catches it, it looks at its own internal clock to measure the difference.
Right. So if the signal left the satellite at exactly noon, and your receiver catches it 1/10 of a second after noon, you multiply that 1/10 of a second by the speed of light.
And that calculation gives you the exact distance between you and that specific satellite.
Which is referred to as the pseudo-range.
Okay, so once I have that distance, the geometry is pretty straightforward. If I'm 12,000 miles from satellite Alpha, I have to be somewhere on a giant imaginary sphere with a radius of 12,000 miles.
With satellite Alpha right at the center. But you could be anywhere on that massive sphere.
Right, so then I repeat the process with a second satellite. I calculate the pseudo-range to satellite Bravo, drawing a second giant sphere.
And where those two spheres physically intersect, it creates a two-dimensional circle. Now you know you're somewhere in the line of that circle.
Then I pull the signal from satellite Charlie. The third sphere intersects the circle, narrowing it down to just 2 distinct points in space.
And usually one of those points is way out in deep space, or implies you're moving at millions of miles an hour.
So my receiver's computer just rejects the crazy one.
Exactly. The remaining point is your exact location on the surface of the Earth. This process is called trilateration.
Trilateration, the geometric intersection of spherical distances. But wait, trilateration inherently only needs 3 spheres to find a specific point in 3-dimensional space.
Mathematically, yes.
Yet every textbook, including our sources today, says you absolutely must have a clear line of sight to a minimum of 4 satellites for a valid location fix. Why is the 4th one mandatory?
That is the greatest engineering hurdle of the entire system. Perfection of timekeeping.
Timekeeping.
Yeah. To calculate your location in 3D space, your receiver isn't actually solving for 3 variables. It's solving for 4. Latitude, longitude, altitude, and time.
Oh, because the radio wave is moving at 186,000 miles per second?
Right. If the clock inside your receiver is off by even 1 single millisecond, 1/1000th of a second, your calculated distance is going to be incorrect by nearly 200 miles.
200 miles from 1 millisecond of error? That's insane.
Exactly. Now, the satellites in orbit carry multi-billion-dollar atomic clocks that are incredibly precise.
But the phone in my pocket definitely doesn't have an atomic clock in it.
Right, nor does the ruggedized receiver bolted to a military Humvee. Those rely on cheap, mass-produced quartz crystal clocks.
And quartz clocks constantly drift. They are never perfectly synchronized with the atomic clocks in space.
Which means the lightning and thunder math is broken right from the start. Their clock is running a millisecond fast, so the time delay calculation is wrong, the sphere radius is wrong.
And if all 3 spheres are the wrong size, they aren't going to intersect perfectly. They'll just overlap into a messy, blurred triangle.
Exactly. And that blurred triangle of error is where the 4th satellite comes in.
So what does the 4th one do?
The receiver pulls the pseudo-range from that 4th satellite, realizes the 4 spheres don't intersect perfectly, and mathematically deduces that the error is caused by its own cheap quartz clock.
Oh, I see. It assumes its true location is where they should all meet, and uses the 4th satellite as a mathematical key to reverse engineer the correct time.
Precisely. It adjusts its own internal quartz clock backward or forward until the distances from all 4 satellites snap into perfect geometric alignment at a single point.
That is so smart. So not only does the receiver discover its physical location, but it simultaneously perfectly synchronizes its cheap clock with a multi-million-dollar atomic clock in space.
It's a dual-use triumph. And as we'll see, that perfect time synchronization is huge. But to keep all this math working, the military has to manage a massive global architecture.
Right. The United States Army Space Reference Text breaks this architecture down into 3 distinct pillars, or segments. The first one is the space segment.
The physical constellation of satellites itself.
And these satellites aren't just skimming the atmosphere in low Earth orbit, and they aren't way out in distant geosynchronous orbit either.
No, they operate in a very specific regime called medium Earth orbit.
So how high up is medium Earth orbit?
For this constellation, it sits at roughly 12,500 miles above the Earth's surface.
And at that specific altitude, orbital mechanics dictate that it takes exactly 12 hours to complete one revolution around the planet.
Right. And they didn't just throw them up there randomly. The military arranged them into 6 distinct orbital planes.
Which is kind of like a fixed track, right? Like a massive hula hoop encircling the globe.
A good analogy. They used 6 of these hula hoops, tilted at a 55-degree inclination relative to the equator, evenly spaced around the Earth.
By spacing multiple satellites evenly along each of those intersecting planes, they guarantee this massive overlapping footprint of coverage.
Right. It ensures that whether you're an infantryman in a deep valley in Afghanistan, a destroyer in the Pacific, or a civilian walking through Manhattan, you will always have an unobstructed line of sight to at least 4 satellites.
The baseline requirement for a 3-dimensional fix, day or night.
Always.
But why put them 12,500 miles away? Wouldn't the signal be stronger if they were in low Earth orbit?
It would be. And a stronger signal would be much harder for an enemy to jam. But a satellite in low Earth orbit has to travel at roughly 17,000 miles per hour just to stay in orbit.
Oh, so it would just streak across the sky and disappear over the horizon in like 10 minutes.
Exactly. A receiver on the ground would constantly lose connection and have to desperately search for a new satellite. Plus, from that low altitude, a satellite's field of view is tiny.
So to guarantee 4 satellites are always visible from anywhere on Earth, you'd need hundreds or maybe thousands of satellites.
Which was completely financially and logistically impossible in the 1970s.
Right. Okay, what about geosynchronous orbit, 22,000 miles up? They basically hover over one spot there.
True. You'd only need 3 or 4 satellites to cover the whole globe. But at that extreme distance, the radio signal reaching your phone would be almost imperceptibly weak.
And because of the curvature of the Earth, coverage at the extreme northern and southern latitudes would be terrible.
Right. So medium Earth orbit is the ultimate Goldilocks zone. It provides a massive field of view, allowing a baseline constellation of just 24 satellites to cover the planet, while keeping them close enough that a small antenna can still catch the whisper of the signal.
But operating that constellation requires constant management, which brings us to the second pillar, the ground segment. Space is a pretty violent environment, right?
Highly volatile.
Yeah.
The Earth isn't even a perfect sphere of gravity. The equatorial bulge creates gravitational unevenness called the J2 effect.
And the gravity from the moon and the sun are constantly tugging on the spacecraft too?
Even the physical pressure of photons striking the solar panels, solar radiation acts like a microscopic wind, slowly pushing the satellite off its path.
Which means the intricate math of trilateration we just talked about is constantly degrading. If a satellite gets pushed 50 feet out of its slot, the receiver on the ground is using faulty geometry.
The spheres are originating from the wrong location. Correcting that is the job of the Master Control Station at Schriever Space Force Base in Colorado.
They're the brain of the whole architecture.
Yeah, they command this global network of highly sensitive monitor stations and massive ground antennas. The monitor stations passively track the satellites 24 hours a day,
Measuring exactly where they physically are and checking for any microscopic drift in their onboard atomic clocks.
Then the Master Control Station compares where the satellite actually is to where it mathematically should be and calculates a highly precise correction.
And they beam that updated navigational data and clock correction right up to the satellite using those ground antennas.
The satellite takes that data package and seamlessly weaves those corrections into the signal it broadcasts back down to Earth.
It's a relentless feedback loop, because if the ground segment went offline and those daily updates stopped, the errors from gravity and clock drift would compound exponentially.
The system's accuracy would degrade from inches to miles in a matter of weeks. It would be tactically useless.
So we have the space segment and the ground segment. The physical link connecting them to the user on the ground is the third pillar, the link segment.
This is the invisible radio wave itself. The satellites transmit data across specific frequencies in the L-band of the radio spectrum.
The doctrine heavily references 2 primary legacy frequencies, L1 and L2.
Right, and using the L-band is very intentional. Those specific frequencies can penetrate dense cloud cover, heavy rain, and the atmosphere with minimal degradation.
All-weather reliability. But they aren't just blasting a single continuous tone, are they?
No, they use a highly complex technique called spread spectrum communication. The navigation data is modulated onto the carrier wave using specific ranging codes.
And the United States Army Space Reference Text highlights a really critical split in these codes. There's a big division between civilian capabilities and military requirements.
Yeah, so the satellites broadcast a course acquisition code, which is unencrypted and freely available to the public.
The course acquisition code is basically the backbone of the modern global economy. That's the signal your smartphone uses.
Commercial airliners navigating the Atlantic, agricultural combines precisely planting seeds, global shipping fleets, they all use it.
It's designed to be super easy and fast for any commercial receiver to pick up. But the military needs something stronger for hostile environments.
Right. So alongside the civilian signal, the satellites broadcast a precision encrypted code.
And only authorized military receivers with highly classified cryptographic keys can actually decipher that precision code. It provides slightly enhanced accuracy, sure, but its true value is security.
Exactly. It's the first line of defense against electronic warfare. It stops an adversary from feeding false coordinates to an allied weapon system, which is called spoofing. And we'll get into that terrifying concept later.
Definitely. Exploring these three segments, space, ground, link, really shows the sheer scale of the engineering. But the doctrine actually drops a pretty surprising revelation.
The name itself: positioning, navigation, and timing.
Right. The public is totally fixated on the positioning and navigation part. We think of it as a global compass.
But from a strategic and infrastructural standpoint, the timing aspect is arguably the most critical and the most vulnerable element of the whole system.
Within defense and engineering circles, they view the constellation less as a navigation tool and more as a globally accessible, universally synchronized clock.
Because, as we established with the whole trilateration math, finding your location inherently forces your receiver to perfectly synchronize its internal clock with the atomic clocks in space.
Once that correction happens, your phone is no longer just a map. It's a timepiece synchronized to the absolute master timescale, accurate down to the nanosecond.
Driven by the most perfect chronometers ever engineered by human beings. The physics behind those clocks literally reads like science fiction.
They use elements like rubidium and cesium, right?
Yeah, the atomic clocks in the satellites don't rely on a swinging pendulum or a vibrating quartz crystal. They operate on quantum mechanics. They measure the incredibly stable resonance frequency of specific atoms.
So how does that actually work with cesium?
Well, when a cesium-133 atom is bombarded with a specific frequency of microwave radiation, its outermost electron transitions between energy states.
And that transition happens at a very exact rate.
An unvarying rate. Exactly 9,192,631,770 times per second.
Wow. And because it's quantum physics, that rate never changes.
Right. A cesium atom will oscillate at that exact frequency, whether it's in a shielded lab deep underground in Colorado or hurtling through the vacuum of space 12,000 miles up.
By electronically counting those exact atomic transitions, the clock maintains perfect accuracy over immense periods of time.
And the constellation distributes that quantum perfection to the entire globe.
That nanosecond precision is completely vital for modern military communications. Because tactical military units don't just tune their radios to a single static frequency and talk in the open.
No, an adversary could just listen in or drop a jammer on that frequency. Instead, they use secure frequency hopping.
Right. A tactical radio rapidly changes its transmission frequency hundreds of times a second, jumping across a wide spectrum in a pseudo-random pattern.
Which makes it incredibly difficult for an enemy to intercept or jam. But for it to work, the receiving radio has to jump to the exact same frequency at the exact same fraction of a millisecond.
If they're out of sync by even a fraction of a second, the receiver just hears static.
They have to be perfectly choreographed. And the timing signal cascading down from the satellites is the universal metronome that choreographs that entire dance across the joint force.
If an enemy degrades that timing signal, secure tactical communications start to fracture.
And that vulnerability extends way beyond the battlefield. The modern global economy is fundamentally addicted to this timing signal.
High-frequency trading algorithms execute thousands of stock transactions per second. Every single trade has to be time-stamped with absolute precision to ensure the correct order of execution.
It prevents massive financial fraud and seamlessly synchronizes banking databases across continents.
So when you buy a cup of coffee with a credit card, the banking network verifying it is relying on a timestamp generated by the radioactive decay of a cesium atom floating in medium Earth orbit.
It's crazy to think about. And the global power grid relies on it too. They use phase measurement units synced by the timing signal to perfectly manage the flow of alternating current across thousands of miles of lines.
If that synchronization drifts, sections of the grid can experience destructive interference, cascading blackouts.
Cellular telephone networks rely on it to seamlessly hand off your phone call from one cell tower to the next while you're driving on the highway. Lose the signal, calls just drop.
It's quite literally the heartbeat of the modern world. But there is another hidden capability woven into this architecture.
Oh yeah, the secondary payloads.
Right. The United States Army Space Reference Text explicitly highlights this, and it has absolutely nothing to do with navigation or civilian infrastructure.
Nuclear detonation detection.
It's this highly classified legacy of the Cold War. In the 60s, the military launched the Vela satellite program specifically to monitor global compliance with the Partial Test Ban Treaty.
They needed an orbital vantage point to detect any atmospheric or space-based nuclear explosions. And as the modern navigation constellation was being developed, they realized it was the perfect host platform for these sensors.
Because the satellites are in medium Earth orbit, each one has a massive hemispheric view of the Earth.
And when you combine 24 of them into a unified constellation, you have an impenetrable overlapping web of surveillance covering every inch of the globe, 24/7.
The specialized sensors bolted to these satellites are engineered to detect the specific signatures of a nuclear detonation.
Because a nuclear explosion doesn't just look like a big conventional bomb. It produces a very distinct, double-peaked optical flash.
An intense burst of light, a brief dimming as the shockwave obscures the fireball, and then a second massive expansion of light.
Right, and that flash is measured by optical sensors called bang meters. The payloads also detect the immediate burst of X-rays and the massive electromagnetic pulse.
When a nuclear device goes off anywhere, multiple satellites instantly detect those signatures.
And this is where the genius of the architecture really shines. Because the satellites are perfectly synchronized in time.
Thanks to the cesium.
Exactly. The system can measure the microscopic differences in the exact moment the optical flash reached each individual satellite.
Oh, so they just run the trilateration math in reverse.
You got it. By applying the exact same math backwards, the system pinpoints the precise location of the nuclear detonation on the surface of the Earth.
Providing national command authorities with immediate, actionable intelligence. It's just a staggering convergence of capabilities. Atomic chronometers enabling stock trades, optical sensors scanning for nuclear war, all sharing the same physical chassis.
But as perfectly engineered as the space segment is, the radio signal still has to survive a brutal 12,000-mile journey through the physical environment to reach your phone.
And the doctrine dedicates a lot of focus to the errors introduced during that journey and the advanced augmentation required to correct them.
Operating in the physical domain is inherently messy. The greatest natural adversary to the satellite signal is the Earth's ionosphere.
The ionosphere is this thick layer of the upper atmosphere, from roughly 40 miles to 600 miles up, where intense ultraviolet radiation from the sun strips electrons from gas atoms.
It creates a dense, highly volatile soup of electrically charged plasma. And remember, the speed of light is only a constant in a perfect vacuum.
And the ionosphere is definitely not a vacuum. When the fragile radio signal hits that plasma, it physically interacts with the electrons.
Refraction bends the trajectory of the wave and physically slows down its transit speed. The density of that plasma fluctuates based on solar activity, time of day, and geography.
That variable density is known as the total electron content. The higher the total electron content, the more the signal is delayed.
And returning to our foundational equation, if the signal is delayed by the plasma, your receiver's time measurement is wrong.
Which means the calculated distance to the satellite is wrong, the sphere is the wrong size, and the glowing blue dot on your screen drifts significantly away from your actual location.
The ionosphere is the largest single source of natural mathematical error in the whole architecture. But beyond the atmosphere, you also have to deal with terrestrial obstacles.
Multipath error. This one completely wreaks havoc in dense urban environments or really mountainous terrain.
It's essentially an electromagnetic echo.
Right. Imagine standing at the bottom of a deep rock canyon. If someone at the rim shouts your name, you probably don't hear their voice traveling directly to your ear.
No, the sound wave bounces off the canyon wall to your left, then reflects off the right wall before finally reaching you.
The overlapping echoes make it incredibly hard for your brain to pinpoint exactly where they are standing.
The radio signal experiences the exact same phenomenon. The wave comes down, But instead of a clean, direct line of sight into the receiver's antenna, it violently reflects off the glass and steel of a skyscraper.
Or deflects off the granite face of a mountain. So the receiver catches the reflected echo of the signal.
And because it had to travel a longer angular path to bounce off the building, it arrives a tiny fraction of a second later than the direct signal would have.
The receiver incorporates that delayed arrival time into its math, the pseudo-range stretches, and the location fix is totally thrown off, sometimes by hundreds of feet.
Now, 100 feet of error is a mild inconvenience if you're just looking for a coffee shop.
But it's catastrophic for a commercial airliner attempting an instrument landing in dense fog.
Or for a smart munition trying to strike a specific bunker. So to get that absolute precision, engineers developed sophisticated augmentation systems.
The civilian sector relies heavily on the Wide Area Augmentation System, operated by the Federal Aviation Administration.
The architecture here is brilliant. They built a massive network of highly precise, physically surveyed reference stations across the entire North American continent.
They essentially reverse engineer the error. Because these physical reference stations are bolted to the ground in concrete, their exact geographic coordinates are known with unyielding certainty.
Right. The station listens to the incoming satellite signals and calculates its position based on the pseudo-range math. Then it compares its mathematical location against its known physical location.
If the math tells the station it's 10 feet further west than its physical concrete pillar, the station immediately deduces that the ionosphere directly above it is currently dense enough to cause exactly 10 feet of delay.
The stations transmit these continuous error calculations to master processing centers. They compile a highly detailed, real-time map of the ionospheric delay across the entire continent.
That correction data is beamed up to a separate set of commercial geostationary satellites which broadcast the fix back down to user receivers.
Your receiver pulls the raw navigation signal, pulls the correction data, and mathematically cancels out the atmospheric delay. Pinpoint accuracy restored.
It's an incredible feat of civil engineering, but it relies on a vulnerable, fixed network of ground stations. A military unit operating deep behind enemy lines can't rely on a civilian augmentation network.
No, the military had to engineer a self-contained solution. They leverage a fundamental law of plasma physics. The ionosphere is a dispersive medium.
Meaning the charged plasma slows down different frequencies of radio waves by different predictable amounts.
Exactly. This is why the military architecture broadcasts the link segment on two distinct frequencies, L1 and L2.
A civilian receiver usually only listens to the L1 frequency, making it totally blind to the exact density of the plasma. But a military receiver is dual frequency.
It listens to L1 and L2 simultaneously. And because the two frequencies are bent and delayed by different amounts passing through the exact same patch of ionosphere, the military receiver just measures the microscopic difference in their arrival times.
By measuring that delta, the computer instantly calculates the exact total electron content directly above it.
It solves algebraic equations in real time, internally without any external reference stations, mathematically subtracts the delay, achieving staggering accuracy autonomously.
And that self-contained precision is the foundation for tactical applications like the dismounted assured positioning, navigation, and timing system.
Historically, an infantry soldier in a jungle canopy or urban combat zone relied on commercial-style receivers, very susceptible to multipath errors and easily jammed.
But the modern battlefield requires every soldier to be a precision node in a massive digital network.
Integration of dual-frequency capabilities, access to the encrypted precision code, and pairing external signals with internal physical sensors ensures they always know their exact coordinates.
And seamlessly feeds those coordinates into the joint common operating picture, allowing commanders to perfectly track forces and coordinate complex multi-domain fires.
The impact of this precision on field artillery represents a total paradigm shift in military doctrine. Throughout the 20th century, field artillery was fundamentally an area weapon system.
You'd fire hundreds of unguided high-explosive shells into a grid square, hoping the statistical distribution of impacts would eventually destroy the target.
Which requires a massive logistical tail. Transporting thousands of heavy artillery shells to the front lines is dangerous and slow. Plus, dropping hundreds of shells exponentially increases the risk of catastrophic collateral damage.
But bolting hardened navigation receivers into the nose cones of artillery shells completely reversed that doctrine.
Today, a commander fires a single precision-guided munition. As the shell travels along its ballistic arc, it acquires the satellite signal, calculates its exact position in 3D space.
And uses small aerodynamic fins to actively steer itself through the atmosphere, landing within mere feet of the designated coordinates.
A target that previously required an entire battery firing hundreds of rounds can now be eliminated with a single shell. Reduced logistical burden, preserved stockpiles, minimal collateral damage.
The precision is devastating, but that reliance on devastating precision introduces the greatest strategic vulnerability of the modern era.
Because the entire joint force, the soldier, the smart shell, the communications network, is entirely dependent on this incredibly fragile radio signal.
Adversaries have recognized the shortcut. You don't need to spend trillions building a massive stealth bomber fleet to defeat the United States. You just neutralize the invisible timing and navigation signals.
Blind the joint force, and the multi-domain architecture collapses. This birthed an entirely new domain of strategic competition.
Joint Publication 314, Joint Space Operations, officially designates this battleground as navigation warfare.
Deliberate defensive and offensive actions executed to assure friendly use of positioning data while preventing adversary use of that same data. It requires synchronized space forces, cyberspace ops, and advanced electromagnetic warfare.
To understand the offensive tactics, you have to think about the physics of the signal itself. The satellites are 12,500 miles away, operating on solar power.
By the time that radio wave penetrates the atmosphere, the signal strength is incredibly weak.
In engineering terms, it's roughly negative 160 decibel watts.
Which is abstract, but it's roughly equivalent to looking at the visual brightness of a single 50-watt light bulb from 10,000 miles away.
The receiver's antenna is straining to hear an absolute whisper of electromagnetic energy.
Because it's a whisper, the most rudimentary form of navigation warfare is simply jamming. An adversary just builds a radio transmitter that blasts a massive wall of raw electromagnetic noise on the exact L-band frequencies.
It's the equivalent of someone standing next to you with a pressurized air horn while you try to listen to a friend whispering from across a crowded stadium.
The antenna is totally overwhelmed. Tracking loops fail, pseudo-range math collapses, and the blue dot simply vanishes. Jammers can range from small battery-operated devices to massive truck-mounted military arrays, denying hundreds of square miles of airspace.
Jamming is an effective denial tactic, but the adversary is explicitly announcing they are there. When the screen goes blank, you know you are under an electronic warfare attack.
Right, which brings us to a significantly more insidious threat: spoofing.
Spoofing moves beyond denial into active deception. If jamming is drowning out the whisper with an air horn, spoofing is having an adversary stand directly over your shoulder and flawlessly mimic your friend's whisper to feed you a continuous stream of lies.
The spoofing device generates a perfectly structured, mathematically valid counterfeit satellite signal and broadcasts it at a power level just slightly higher than the authentic signal from space.
The receiver catches the fake signal, drops the authentic one, and locks onto the counterfeit transmission. The screen doesn't go blank, no alarm sound.
The operator believes the system is functioning perfectly. But once the spoofer captures the receiver's tracking loops, the spoofing algorithm slowly and subtly alters the timestamps embedded in the counterfeit signal.
The receiver recalculates the pseudo-ranges based on false timing data. Gradually, mathematically calculates that it's moving, even if the physical vehicle is totally stationary.
The tactical implications are terrifying. You could slowly alter the time packets to trick a commercial oil tanker into steering directly into hostile territorial waters,
sparking a massive international incident. Or capture the signal of an autonomous drone and command it to land smoothly on a hostile runway.
Defending against spoofing is exactly why the military relies heavily on the precision encrypted code. Without the classified cryptographic keys, an adversary cannot generate a valid counterfeit of the precision signal.
But as civilian infrastructure becomes increasingly reliant on unencrypted signals, the threat of spoofing to the global economy is massive.
And the geopolitical reality of space is totally fractured. The United States used to have an absolute monopoly on satellite navigation.
Right. The United States Army Space Reference Text makes it clear that monopoly has evaporated. We are now in a multipolar environment where global competitors have launched their own sovereign constellations.
Russia operates the Global Navigation Satellite System, known as GLULOX, developed during the Cold War. It uses a different signal architecture frequency division rather than code division, but it provides a robust global capability today.
The European Union constructed Galileo because they didn't want to rely entirely on a military system controlled by the Pentagon.
Galileo is unique because it's under civilian governance. But its brilliant aspect is interoperability with the American constellation. Modern receivers track both simultaneously, increasing physical accuracy and hardening against localized jamming.
And the most significant strategic shift is China's Beidou system. They realized relying on an American signal was a huge strategic vulnerability in the Pacific.
Beidou is a towering aerospace achievement, and it integrates a unique short message service directly into the navigation architecture.
So a Beidou receiver can actually transmit brief bursts of text data back up through the satellites.
Yes, providing Chinese maritime fleets or military units in deep valleys a sovereign, assured method of reporting their exact position and status back to command.
And nations are also developing regional systems for very specific geographic challenges. Japan constructed the quasi-zenith satellite system.
Right, because their issue is topography. Deep natural valleys and massive hyperdense urban canyons in cities like Tokyo.
A medium Earth orbit satellite low on the horizon is practically useless in Tokyo. The signal is completely blocked by skyscrapers.
So Japan engineered a highly elliptical, asymmetrical orbit. The satellites trace an elongated figure 8 over the Asian-Pacific region,
drastically slowing down when it reaches the top of its arc over Japan. It essentially loiters almost perfectly straight up in the zenith for hours,
guaranteeing a receiver deep in an urban canyon can look straight up, avoid the skyscrapers entirely, and maintain a pristine line of sight. India has a similar regional architecture for the subcontinent.
So when you look at this entire landscape strategically, the physical weakness of the signal, cheap jammers spoofing algorithms and competitor constellations, it begs a terrifying doctrinal question.
Has the modern military built its entire operational architecture around a single catastrophic point of failure? Are we walking into a trap assuming the blue dot will always be there?
That vulnerability drives modern military engineering. The Joint Force knows that in a peer-to-peer conflict, the navigation signal will be relentlessly degraded.
Navigation warfare requires bridging that gap, ensuring platforms operate in a totally denied electromagnetic environment. The primary technological bridge is the inertial navigation system,
which strips away the reliance on external space completely. No antenna, no listening for radio whispers, a totally self-contained, closed-loop physical system.
It relies on internal sensors, ring laser gyroscopes, and highly sensitive physical accelerometers, measuring rotational forces and the exact physical force of acceleration along a 3D axis.
If you tell the computer its exact, perfectly known starting location, it just monitors the accelerometers, mathematically calculates how fast it moved, what direction, and for how long,
continuously calculating its current location relative to where it started. If a stealth bomber hits a massive wall of enemy jamming, the pilot doesn't lose navigation. The computer seamlessly switches to the inertial navigation system.
But it's not perfect. Any microscopic physical imperfection in the gyroscope introduces a tiny mathematical error, and over time, those errors compound. The position drifts.
To combat drift, it has to periodically receive a precise update to recalibrate. To get those updates in a jammed environment, the military employs controlled reception pattern antennas.
These are dynamic computational arrays. They utilize spatial processing to actively shape how they listen to the environment.
If an enemy jammer is blasting noise from a ridgeline, the antenna rapidly analyzes the phase of the incoming noise and mathematically alters its reception pattern to create a null in that specific direction.
It effectively places an electromagnetic blinder over its own ear, completely ignoring the noise from the horizon, while electronically amplifying its sensitivity straight up to catch the faint whisper of the satellite.
The internal resilience of the inertial navigation system, continually corrected by the digitally filtered precision of the anti-jam antenna, forms the baseline of modern tactical survivability.
But the defensive mindset is shifting. The United States Army Space Reference Text hints that the future relies on a massive evolutionary leap. Relying solely on a handful of massive satellites in medium Earth orbit is a legacy approach.
The future of assured navigation lies in the proliferation of low Earth orbit.
We established earlier that doing that in the 70s was financially impossible. But reusable rockets have completely plummeted the cost of launching mass into orbit.
And electronics have miniaturized. We are mass-producing highly capable satellites the size of a dishwasher now.
Commercial companies are launching mega constellations into low Earth orbit to provide global broadband internet. And the military views that dense commercial web as the ultimate strategic opportunity.
The tactical logic is unassailable. The military doesn't need to launch a dedicated, expensive constellation. They just piggyback encrypted navigation payloads onto the thousands of commercial communication satellites already up there.
And because low Earth orbit is only 300 miles away, the radio signal reaching the ground is hundreds of times stronger. It ceases to be a whisper. It becomes a roar.
Drowning out that signal requires an adversary to deploy a jammer so massively powerful that it instantly becomes a glowing target for an anti-radiation missile.
Furthermore, the sheer volume of satellites creates unparalleled resilience. If an adversary destroys 3 or 4 satellites in medium Earth orbit, the legacy system degrades significantly.
But if you have a proliferated web of 3,000 satellites in low Earth orbit and an enemy shoots down 10 of them, the network simply uses artificial intelligence algorithms to dynamically route the data around the damage.
The loss of individual nodes becomes statistically irrelevant. The evolution from a fragile, static architecture into a dynamic, artificial intelligence-driven web is staggering.
We really have covered an immense expanse of history, physics, and doctrine today.
We did. We started with Cold War pressures, forcing the Navy to measure Doppler shifts just to hide submarines. We broke down the physical science of trilateration.
The space segment in the Goldilocks zone, the ground segment battling orbital degradation, and the encrypted link segment.
The quantum mechanics of atomic clocks synchronizing tactical radios and orchestrating high-frequency stock trades. The secondary mission of detecting nuclear detonations.
The chaotic reality of ionospheric plasma and multipath echoes, and how systems like the Wide Area Augmentation System and dual-frequency military receivers mathematically defeat them to guide smart artillery.
And finally, navigation warfare. The brute force of jamming, the deception of spoofing sovereign competitor constellations, and the tactical bridges of ring laser gyroscopes and low Earth orbit mega constellations.
Tracing this from a rudimentary 2D tracking tool into the fundamental metronome of human civilization has been a remarkable journey. But it leaves us with a highly provocative final thought.
Right. What is the ultimate tactical thought experiment we are leaving the listener with today?
As commercial aerospace companies aggressively launch tens of thousands of interlinked communication satellites into low orbits, we must ask, will the massive, expensive, traditional medium Earth orbit navigation constellations eventually become entirely obsolete? Or will the military of the future dynamically bounce heavily encrypted positioning signals across thousands of commercial networks, using artificial intelligence to constantly change frequencies and routing paths in milliseconds, effectively making our global navigation architecture completely invisible, decentralized, and mathematically impossible for any adversary to ever jam?
The concept of the infrastructure dissolving into a completely fluid, artificial intelligence-driven web of signals bouncing unpredictably across commercial internet satellites is wild. It forces you to realize that the glowing blue dot on your phone is not merely a modern convenience. It's the visible artifact of an ongoing, silent, global battleground. The magic of locating yourself in the world truly has become the most critical infrastructure we possess. And it's infinitely more fragile and profoundly more vital than we ever stop to consider when we are simply trying to find our way through an unfamiliar city.